Good evening, students. In last lecture, we discussed on the short columns. We have solved some problem based on the failure of short column by the crushing load. We already discussed on Euler's column theory for the long columns, failure due to the buckling or crippling loads. Okay. Now, solving a problem based on Euler's column theory for the long columns. Problem is a bar of length, 4 meter, when used as a simply supported beam, and subjected to a uniformly distributed load of 30 kilonewton per meter over the whole span. Deflects 15 mm at center. Determine the crippling load when it is used as a column with following conditions. First, both ends pin jointed. Second, one end fixed, other end hinged. Third, both end fixed. A bar of length 4 meter when used as simply supported beam and subjected to uniformly distributed load of 30 kilonewton per meter over the whole span. Beam deflects by 15 mm at center. Determine the crippling load when it is used as a column with following conditions. First, both ends pin jointed. Second, one end fixed, other end hinged. And when both the ends are fixed. First of all, write down the data which is given in the numerical. The length of the bar has been given 4 meters. Uniformly distributed load is equal to the 30 kilonewton per meter. Deflection has been given at the center of the beam 15 mm, or say 0.15 meters. Sorry, 0.015 meters. As we know that maximum deflection for a simply supported beam having a uniformly distributed load at its whole span is equal to the 5 WL to the power 4 divided by 384 EI. Here deflection has been given 0.015 meters. Uniformly distributed load is given 30 kilonewton per meter, or say 30 into 10 to the power 3 newton per meter. Length of the beam is 4 meters divided by E into I. Okay, we have to determine this flexural rigidity into I from this equation. E into I will be equal to the it will be equal to the 6.66 into 10 to the power 6 Newton meter square. This is the flexural rigidity of this beam, which is used as a column for different end conditions. First, when both the ends are pin jointed, in that case the crippling load will be equal to the pi square EI upon L square. So from here, flexural rigidity is 6.66 into 10 to the power 6 divided by 4 to the power 2. Now the crippling load for the column having both the ends are pin jointed will be 4108 kilonewton. Similarly, we can calculate the crippling load by the Euler's equation for the column having one end fixed and other end is hinged. In that case, the crippling load will be equal to the 2 pi square EI upon L square. Flexural rigidity is 6.66 into 10 to the power 6 divided by 4 to the power 2. P is equal to the 8207 kilonewtons. And crippling load when the both the ends are fixed will be equal to 4 pi square EI upon L square. It will be equal to the 16,432 kilonewton. Okay. Now we have discussed about the failure of long columns and the failure of the short columns. The failure will occur in short columns due to the crushing load, and if the eccentric load is applied in a short column, in that case a bending moment will generate about the section of the column, and due to which bending stresses are induced in the section. So in the case of a short column, the total stress will be equal to the direct stress plus bending stresses, which is induced due to the eccentric load. And in the case of a long column, failure will occur due to the buckling alone, because uh, the length of the column compared to the cross section dimensions of the column are very large. So the buckling load is lower than the crushing load. It means for crushing the material of the long column, the the magnitude of the load required is much greater than the load required for the buckling of the given column. So when we applying the load on a long column, in that case buckling will occur firstly, because the magnitude of the buckling load in comparison to the crushing load is very small. So the long column fails due to the buckling only, buckling alone. We can determine the calculate the buckling load for the columns having different end conditions by the Euler's column theory, Euler's column equations. Uh, the crippling load for a long column having both the ends are fixed uh, will be equal to the pi square EI upon L square. And when the both the ends are when the both the ends are pin jointed, in that case the Euler's buckling load by the Euler's equation will be pi square EI upon L square. If the both the ends are fixed, in that case the buckling load will be equal to the 4 pi square EI upon L square. And if the one end is fixed and other end is free, in that case the buckling load will be equal to pi square EI upon 4L square. And for the column whose one end is fixed and other end is pin jointed, in that case the buckling load will be equal to the 2 pi square EI upon L square, as we already discussed in previous lectures. Uh, Now, failure in a column or in a medium size column. Okay. So, in the case of a medium size column, failure will occur by the combined effect of the crushing and the buckling. We cannot confirm that the failure in a medium column is occurred due to the uh, crushing or due to the buckling. Okay, both the factors are included in the failure of the medium sized column. So determining the load, magnitude of load at which the medium sized column has been failed, we can calculate the failure of a medium sized column by the Rankine's formula. Okay, what is Rankine formula? As we know that for a short column, crushing load will be equal to the crushing stress into cross sectional area of the column, and if the sigma c is the maximum possible compressive stress and A is the sectional area, then the compressive load, crushing load will be equal to sigma c into A. Now, for a long column, we know that crippling load by the Euler's equation will be equal to pi square EI upon LE square, where L is the equivalent length of the column. Now we know that moment of inertia will be equal to the AK square, where A is the cross sectional area of the section and K is the least radius of gyration. Then PE will be equal to the pi square E into AK square by LE square. Crippling load will be equal to the pi square E into A K upon LE square. Now, according to the Rankine hypothesis, is failure in medium column will occur if at the load P, in that case it will be equal to the 1 by P is equal to the 1 by failure due to the crushing load plus 1 upon failure due to the buckling load. See, what will be the actual concept behind this equation? If column is a short column and buckling will occur due to the crushing, because as we know that the failure will occur in short columns due to the crushing. In that case, crushing load will be very small in comparison to the buckling load, because if the length of the column is small, in that case crippling load is very large in comparison to the crushing load. Or in other ways, crushing buckling will be occurred in a short column at a very large amount of load. If crushing load is very small and in comparison to crippling load for a in the case for a short column, in that case 1 by P upon 1 by Pc plus 1 by Pe, here 1 by Pe will be less than 0. Okay, the magnitude of this 1 by P will be very small in comparison to 1 by Pc, because 1 by Pc is very small in comparison to P. Hence, the failure in the column will be due to the crushing load, because the column is a short column. Okay. Now, in the case of a long column, crushing load is high in comparison to the buckling load. So again, here 1 by Pc will be less than 0 and 1 by Pe. So the failure, because as we know that the failure will occur due to the crippling load in the case of a long column, then the failure load at which the column will fails equals to the crushing load, buckling load. So according to the Rankine hypothesis, 1 by P will be equal to the 1 by crushing load plus 1 by crippling load. If the strut is very short, so again, if the strut is very short, then Euler's crippling load will be 1 by P will be equals to 0. So that P is equal to Pc, which is in fact true. Okay. Similarly, for a very long strut, 1 by Pe becomes very large, so that P is equal to the P Eulers. Now, 1 by P is equal to 1 by Pc plus 1 by Pe. One by P is equal to the 1 upon sigma C into A plus 1 upon pi square EA K upon LE square, or A upon P will be equal to the 1 upon sigma C plus 1 upon pi square E K upon LE square. E by A will be equal to the sigma C upon 1 plus sigma C upon pi square E Le by K whole square. For P is equal to the sigma C into A upon 1 plus A Le by K whole square, where A is equal to sigma C upon pi square E. This equation is known as Rankine equation. Now take a problem based on Rankine formula. A hollow cast iron column whose outside diameter is 200 mm has a thickness of 20 mm. It is 4 meter long and fixed at both ends. Calculate the safe load by Rankine Gordon formula. Using a factor of safety of 4, take sigma C is equal to the 550 mega Newton per meter square, and A is equal to the 1 upon 1600. Okay, a hollow cast iron whose diameter is 200 mm, outside diameter is 200 mm, has a thickness of 20 mm. It is 4.5 meter long and fixed at both ends. Calculate the safe load by Rankine Formula using a factor of safety 4. Take sigma c is equal to 550 meganewton per meter square and A is equal to 100, 1 by 1600. Now, first of all, write down the data given in the numerical. First of all, outside diameter. Capital D is equal to 200 mm or 0.2 meters. Thickness of the column has been given. (20 mm). Now the inside diameter of column will be is equal to D minus 2T, 200 minus 2 into 20, so it will be equal to the 160 mm or 0.16 meters. Clear? Length of the column is 4.5 meter. And factor of safety has been given 4. Now the area of the column A will be equal to the pi by 4 capital D square minus small d square, or A will be equal to the pi by 4 0.2 square minus 0.16 square. Area will be equal to 0.0113 meter square. The area of the cross sectional area of the column will be 0.0113 meter square. Now the moment of inertia of the cross section, least moment of inertia, it will be equal to pi by 64. Section is circular, so moment of inertia will be constant about x and y axis. it will be equal to 4.637 into 10 to the power minus 5 meter to the power 4. Now the k square will be equal to the I by A, which is 4.637 into 10 to the power minus 5 divided by 0.0113 equals to the 0.0041 meter square. Here both the ends are fixed, and the equivalent length will be equal to the length of actual column divided by 2. Column length has been given 4.5, then equivalent length will be equal to the 2.25 meters. Now using Rankine formula, which is equal to the P is equal to the sigma C into A divided by 1 plus A LE by K whole square. Sigma C is 550, area is 0.0113 upon 1 plus 1 upon 1600 into 2.25 square divided by 0.0041. It will be equal to 3.51 10 to the power 6 newtons. Now the safe load will be load divided by factor of safety, which is 4. Load is 3.51 into 10 to the power 6 newton divided by 4. It will be equal to 0.877 into 10 to the power 6 newtons, or safe load will be equal to 0.877 meganewtons. Okay. Next numerical. A hollow cylindrical cast iron column is 4 meter long. with both ends fixed, determine the minimum diameter of column if it has to carry a safe load of 250 kilonewton with a factor of safety of 5. Take internal diameter as 0.8 times of external diameter. Take A is equal to the 1 upon 1600 in Rankine formula, and sigma C has been given 550 meganewton per meter square. Length of column L is equal to the 4 meters. Equivalent length for a column whose both the ends are fixed are L is equal to L by 2. It will be equal to 2 meters because actual length of the column is 4 meters. Safe load is 250 kilonewton and factor of safety is 5. If the internal diameter is di or small d, it will be equal to the 0.8 times of external diameter. Sigma C is 550 meganewton per meter square and A is 1 upon 1600. Now, crippling load by the Rankine formula is equal to the safe load into factor of safety. So it will be 250 kilonewton into 5, 750 kilonewton. 1250 kilonewtons. Now from the Rankine formula, sigma C into A divided by 1 plus A LE by K to the power 2. Okay. Moment of inertia will be equal to the pi by 64 d to the power 4 minus small d to the power 4. Cross sectional area of the section will be pi by 4 d square minus d square. K square will be is equal to I by A. So here pi by 64 into 4 upon pi d to the power 4 minus small d to the power 4 divided by d square minus d square. K square will be is equal to the d to the power 2 plus d to the power 2 divided by 16. 1250 into 10 to the power 3 will be sigma c is 550 10 to the power 6. Area is pi by 4 d to the power 2 minus d to the power 2 divided by 1 plus 1 upon 1600 2 upon k to the power 2. One two five zero into 10 to the power 3 will be equal to the now from here capital D will be equal to the 0.136 meters or 136 mm. So small internal diameter will be 0.8 times of external diameter. It will be equal to 108.8 mm. Okay. Thank you very much.